Hortonworks. And with me here is Owen O'Malley, who's one of our founders. He was incidentally the person who wrote most of the first implementation of security for Hadoop.
I did not.
As far back as Jan 2006, and he's been working on MapReduce, Security Hive, ORC, a whole bunch of different projects, and is our founder and technical fellow at Hortonworks. On the Hortonworks side, I used to manage the portfolio of security and governance products, which is Apache Ranger, Apache Knox, Apache Atlas, as well as ODPI. And in the new merged company, we will be carrying forward all of those and adding Apache Sentry, as well as Navigator from the Cloudera side. So lots of interesting times around all of those. But here we're here to talk about different things here. We're here to talk about what's happening in the community in terms of ORC and providing fine-grained column-level encryption as a service within the stack. So let's talk very briefly. I want to do a little bit of setup in terms of the background and hand it off to Owen to dive into the technologies. So when we talk about data protection in Hadoop, these data lakes are now expanding. You have both on-prem data lakes, you have cloud data lakes, you have all kinds of data that's being put in there, structured, unstructured. Here's a little cartoon that shows you like all of the different types of data. You have CRM data, marketing data, demographic data, et cetera, different types of data being put into this data lake environments. And the other dimension to this is that more and more sensitive data is also being added to these data lakes over time. So you see that in the bottom, you see your personal address, name, identity, location, even your health data, as well as community data. So all of these which are considered as personal and protected by GDPR, for example. So we're seeing a lot more of this data within these multiple data lake contexts, and we want to be able to offer the right protection at the right levels across this heterogeneous environment. So you might ask, what's different about this whole big data context? The idea here is that the big data platforms and environments are great for analytics, but they pose a few security challenges. Centralized data lake security as well as multi-tenancy require you to have a consistent model for authentication and fine-grained authorization. The data democratization adds to the complexity and challenges here, because your data scientists, they want to be able to have unfettered access, and they don't like all of the security controls that you may want to impose that are going to keep you out of jail, essentially. So there's a conflict or tension between the democratization angle and the responsible usage of that data within the enterprise. Data is being stored and processed and kept for longer and longer, and you now have this sprawl with cloud and hybrid throwing another dimension to this whole problem, to say you have enough public clouds where your attack surface has now increased quite a bit. If it's within your firewalls and you have a lot more control, you can control that easily. With these hybrid environments, now you have a bigger attack vector that's possible, and also that presents the same type of challenges around authentication and authorization. So the security principles to help solve some of these challenges haven't changed. So we still have a defense in depth, data-centric security, and all of these are becoming even more critical as these market forces are determining how your data is being processed within your enterprises. So let's get to the details here. So let's see this cartoon, once this paints up. Okay, so this is the traditional securing your data lake model. So we always talk about security in layers. So this is our little, I don't know, maybe 13, 14-year-old elephant now sitting in the middle of the castle. You're trying to put different layers of protection around the castle. So we'll go from outside in. So there's a moat. So that is your network segmentation or firewalls. And the way to remember that is without the moat, everything else is moot. So whatever you do, you need to start with the network and protect at that level. Then at the front of the castle, you have this drawbridge, which is your limited access point. That is in our stack, embodied by Apache Knox, which provides authentication, API gateway services, proxying services, as well as single sign-on. At the front door, you have your identity checking process. So these could be your guards who are checking your passports or visas to get into the castle. That's your LDAP or AD. All around the walls, you have these high hard walls. That's your encryption, TLS. There are certain services that are coming from the Cloudera side, in particular KeyTrusty, and then Navigator Encrypt, which is for volume encryption, as well as the Ranger KMS, which is coming from the legacy Hortonworks side. We also have these high watchtowers that are, somebody could go look at all the activity happening within the castle and who's coming, who's going, who's doing what within the castle. So that is your Apache Ranger and Apache Sentry. So Apache Ranger provides you attribute-based access control, authorization, audits, and anonymization capabilities. Within the castle, you have these inner walls. That is your Kerberos to provide your service-to-service and host-to-host protection. So difference in depth, different layers, different technologies, sort of giving you a summary of all of that in one slide. Okay, so what does it mean in terms of data protection? So we have this layered approach. So we have at the bottom level, we have encryption of data at rest, which is your OS level encryption. That could be from LUKS or Navigate and Encrypt, which is a piece of technology coming from the legacy Cloudera side. Then we also have certified partners who provide volume encryption capabilities. And then we have the HDFS transparent data encryption for file and folder level encryption, which is very coarse-grained. That's provided by the key trustee side on the legacy Cloudera and Ranger KMS, and with the ability to offshore or offload the keys into an external hardware security module. Then we also have transport level security. That's encryption of data on the wire. There are several capabilities here. All the wire protocols can be encrypted in the HTTP platform and in the CDH platforms. And there is wire level encryption through different protocols, as well as on the legacy Cloudera side, we have some capability to do what is called auto TLS, which is to manage all the certificates and have those deployments seamlessly use SSL across all of the HTTP traffic. On the more granular data protection side, we have dynamic row filtering and column masking capabilities available via Ranger. There was a talk actually right before this where some of the advances there were kind of discussed. There's also classification-based security that's available via Ranger and Atlas in our stack. And there's also element-level encryption that can be provided by other third-party partners such as Voltage or ProtectReady. So when we talk about encryption, which is the focus of today's conversation here, we have three types of encryption here. There's volume encryption. This is just to protect your disk from physical theft. Your entire volume is encrypted. It's not selective. And of course, it doesn't protect against any other attack vectors via viruses or other areas. The middle level, the application level encryption, which is probably one of the more complex ones, that is where your application itself has the logic to encrypt this data. It gives you the ability to shield this from your rogue admin, for example. And but it's, in practice, it's a lot more complex to implement than volume encryption. Then we also have the third pillar, which is your HDFS at-rest encryption. So this is where you can designate specific folders and files into an encryption zone and manage the keys using the KeyProvider APIs and through Ranger KMS, Key Trustee, et cetera, other services that are available within the stack. So that's the sort of the picture around encryption. Let's look at transparent data encryption. So this is just a very quick sort of summary of this. So we have different levels of keys here. So you have your client, and then the client, that there's keys per file, and there's keys also per encryption zone. The key per file is encrypted with the encrypted version of the zone keys and stored in the file metadata. So there's multiple levels of keys to give you that redundancy, and all of those have to line up for you to be able to decrypt a piece of data. So that gives you selective encryption, gives you the ability to blacklist, for example, your service account such as HDFS admin. So the operators cannot actually see the decrypted data or the clear data in those files. And it's transparent to the application, so all of this decryption happens on the client, on the HDFS side. And the master keys for this whole scheme can be offloaded into a hardware security module such as Gemalto or Thales or one of the cloud providers such as Amazon HSMs. Okay. Very quickly, so this is to talk about row filtering and column masking. So this is available today with Ranger. And this primarily applies to Hive, and a lot of this will be relevant when we talk about the column-specific encryption that Owen will be speaking about next. So what this is showing is the ability for you to have commingled data sets. So in the bottom, you see this table that has different types of data from, let's say, customers across the world, and you have different security policies for depending on who's accessing this under what conditions. So you see on the left here a user from your analyst group, and on the right, a user from an HR group, and they both access and run pretty much the same type of query, and they get to see different results based on the row filter being applied transparently using the range of policies. So this gets you out of the business of maintaining multiple views for these different folks and dynamically being able to insert these predicates and filter the data set down to whatever is appropriate for that context. So this is kind of like a very quick tour through what exists today in terms of encryption and in terms of anonymization. I'll hand it off to Owen to cover the rest of the ORC encryption.
Thanks, Shrikant. So what's the problem? The problem really is that often with the more coarse-grained encryption, that you have a lot of data that needs to be protected differently, but it needs to lay next to each other, right? You've got your customer's social security number next to things like their name that aren't as important. And so you need to actually protect those differently. And it really falls down into all three problems, right? You need to control who can see it, you need to track who has looked at it, and you need to actually encrypt it on disk because of regulatory concerns. And the problem that we had is that file level granularity for protections for those aren't enough, and directory level is even more coarse than that. So we needed to go to the next level down. So we wanted to work in the ORC file format, which we call ORC, and we wanted to make it so that the readers would transparently decrypt the data. So your application didn't need to change at all. And if the user has access to the key, then everything will just work like it did before. And one of the restrictions, of course, is that the data has to be decrypted locally. When you talk to some of the people when they want to, or some of the encryption providers, they want to send all the data back through the KMS. Well, that doesn't work at Hadoop scale. When Hadoop accesses the service, it can easily take it down. I've had customers take down their entire cluster because someone mounted an NFS file through in their job and brought it down. So you can't send all the data through it. It has to be done locally. Furthermore, you only want to decrypt the columns if the user actually needs the column. So for example, if you are accessing 2 fields out of 100, ORC will only read the bytes for those 2 columns. Well, with encryption, in this case, you'll only decrypt the columns that you need to have access for this particular query. And you need to make sure that the master keys are managed securely. You need to make sure that they can be done in hardware and that you have support for key rolling. So very quickly, like Shrikant went through, HDFS encryption gives you transparent encryption, but you've got these encryption zones that are very, very coarse. You end up encrypting everything in a particular directory tree, but other than that, it's very, very convenient. The problem, of course, is it's very coarse. You can only protect things at an entire directory subtree. You can't do things any finer grained than that, so you can't say, okay, we need to protect their social security number or the credit card number, but leave the rest of it available to everyone else. And because all of your data is encrypted, then a lot of users have access to the keys. And with security, that's one of the big concerns, because if everyone has access to the keys, that means that you lose the ability to control that information. Another concern that happens is that move between encryption zones is very painful. So we've been working on fixing them, but Hadoop and Hive in particular is really, really bad about moving the data multiple times. And so you have to be very careful that your temporary space that Hive is writing into isn't in a different encryption zone, because if you move things between encryption zones, it has to completely rewrite the data, which will be very, very slow. The other solution is to use Hive Server 2. Hive Server 2 is what enables all the dynamic masking that Srikanth talked about. But the problem here is that Hive owns all the data. That works great if you're only using Hive, but a lot of our customers want to access the same data from other tools. They want to access their data from Spark or from MapReduce or whichever other tool that they want to access it from. If they've protected it through Hive Server 2, they can't do that. So you've really given up a lot of the pain, or a lot of the capabilities. Now, you can access, actually, these are the old version of the slides. Sorry, we updated the slides a little bit ago, and they apparently got the old version. But the JDBC, where you fetch the results from Hive Server 2, isn't distributed. So your throughput is limited to one machine, and that is a pain. Now, fortunately, the developers for Hive have put a solution in that they can fix a lot of that, and they've made a new connector to LAP. LAP stands for Live Long and Process. How many of you guys have heard about LAP? Oh, good, most of you. And so there's a connector that Spark uses to address that, and so it can fetch the data in bulk. Finally, you can also separate the tables. I've had some customers do this where they put all the personal information into a completely separate table. That allows you to protect the information using HDFS permissions. But the downside, of course, is that now you have to manage those tables, and you have to do joins. So if you've got a terabyte table that you're trying to pull the private information out of, now you're going to have to do a join every time you access that information so that the data is enriched. Finally, there's a pair of encryption UDFs in Hive. I don't recommend using these, actually. The biggest problem is that the keys aren't managed. You actually end up putting the encryption key in the query itself, and the encryption isn't seeded, which means that given the same key and the same value, you'll always end up with the same encrypted bytes. That's actually a really bad property for encryption, because then people can do joins when you don't want them to be able to do joins. So for example, I may be able to not figure out your zip code, but I can join and figure out who else is in the same zip code, which is often undesirable. Okay, so what did we do? So we have, I'm a committer on the ORC project, actually started it. So ORC writes the data into columns. It does that for a column projection so that you can only read the bytes that you need to be able to read, and to give better compression. The reason it gives better compression is because the data in each column tends to be very similar to the other data in that column, and so it compresses much better. So in this model, encryption for columns works really well because you only encrypt the bytes for the column, and you can store multiple variants of the data. This is what it actually looks like. So you can see the file is broken up into stripes with some metadata at the end. Each of the columns is broken up inside. There's both index data and row data. The index data is so that you can quickly skip over the parts of the file that aren't relevant to the query you're working on right now. So what do we do? Or rather, what does the user do when they want to encrypt a file? Fortunately, all they have to do is set some table properties that say which columns they want to encrypt and which keys they want to encrypt it. So for example, in this case, we've said we want to use the PII key to encrypt the social security number and their email, and we want to use the credit key to encrypt the card info. You also need to define where to get the encryption keys, and you do that through a URI. The key management can either go through the Hadoop or Ranger KMS. The KMS, of course, is the key management server. And you create a master key for each use case that you're interested in. So you'd create a PII key and a PCI key and a HIPAA key. And each of those keys would allow you to define who has access to that category of data. And then, as we saw previously, you define the table properties on the columns to define how to encrypt each column and which key. Those, each column would get a unique local key, and you'd use Ranger policies to limit who has access to those keys. So then you could use the Ranger policies that say, Owen has access to the PII keys between 9 to 5, but after that, then he doesn't. And so I could decrypt the data during work hours, but not on the weekends. So that gives you a lot of flexibility. The KeyProvider API is the way that we abstract out how you get the encryption keys. And it takes those local keys and encrypts and decrypts the local keys. The local keys are just random bytes that are chosen for that particular column and that particular file. So the user never gets the master key, basically. So the master key is kept in the KMS and never given out. Now, one of the features that the security people always want is the ability to roll your keys, because they don't want any secrets to be long-term secrets. They want them to be short-term. So you can actually roll the keys, and the ORC Column Encryption will remember which version of the key was used to encrypt the key and use the proper one to decrypt it. And it allows third-party plugins, so you can use Hadoop or Ranger's KMS. You can also use the cloud provider KMS. So if you're running in Amazon, you could use Amazon's KMS. What the flow looks like is you submit your job to the cluster. The user's task will then open up the ORC file, read the encrypted key out of the ORC file. Then he'll pass the encrypted key to the key management server. The decrypted key comes back if they have permission, and then they can read the encrypted data out of the ORC file. So the data doesn't flow through the KMS, but the user never gets the master key that was used to encrypt the local key. That makes sense? The local key is random and for each file. It's managed by the user and the file. The initialization vector is guaranteed to be unique because we set it to the column, the kind, and the stripe counter. So what happens when the user doesn't have access to the key? So we've defined some static masks that correspond to Ranger's dynamic masks. And the default one is nullify. With nullify, all the values become null. So that is a great default behavior, because if you don't have access to someone's personal information, null is actually a really good answer. But we wanted to give some other options. So we gave redact, where you can mask letters to X and numbers to 9. You can actually define how they get replaced. You can also define masks or ranges to leave unmasked. So you can say, for example, if it's a social security number, mask the front part of it, but leave the last 4 digits, so that you can show the user part of the data, but not enough to be identifiable. You can also do things like SHA-256 of the data. Why you'd want to do SHA is if you wanted the users who don't have access to the key to be able to join the data across columns. So if you take someone's social security and put it through SHA, then you can check to see if 2 people are using the same social security number, but not what exactly the social security number is. And finally, we allow a plugin so that you can define your own data masking. Now, one of the challenges with data masking is exactly that you need to be very, very careful. Anonymization is hard. People have messed this up continually. One of the first examples where people messed up was the AOL search logs. If you remember, what happened was AOL wanted to provide their search logs, and they anonymized it. They took out the IP address, but they put in a hash so that you could tell which IP addresses were the same. And that should have been okay, you'd think, right, if you've taken all the user information out. The problem is that people search for themselves, and they search for other things, and so, like their address. So you can verify, hey, if this person is searching for someone who I don't know and isn't very common, and then they search for a center to help some disease, that person probably has that disease. So you've leaked information without intending to. And so you need to be careful with anonymization. The Netflix prize data, they anonymized the Netflix, and they wanted to get machine learning models out of it. But they didn't think about the fact that, oh, people who review movies on Netflix also review movies on IMDb. And so you can join the data sets from an external data set and then find out who the person likely is. Finally, the New York taxi data set, which is a wonderful data set. I love it. Every time someone takes a taxi in New York City, they keep track of where it went from and to and how much they paid. And again, they don't have any identifiable information in there, except that when they record the locations, of course in Manhattan, a 30-foot radius doesn't tell you anything about where anyone is really going, just the rough area. But some of the trips were to places way out into the country, and so you could figure out, hey, if there's only one house anywhere close, you can actually figure out if that was someone going to that particular house. Actually, the first version of the New York taxi data set, they also encoded the medallions of the taxis in MD5. That, in theory, would be okay, except that the medallions are all assigned numerically. So there were 100,000 of them or whatever, and so you just run through the first 100,000, computing MD5s, and suddenly you could completely reverse the masking. So please be careful with masking. Masking is a really challenging topic, and it needs to be considered very carefully. Tokenization is a useful technique. That's one where you just assign arbitrary replacements. So for example, the first user you see gets assigned 1, and the second user you see is assigned 2. There's no meaning there, but that allows joins without leaking any information. Okay, now another use case that's really common is for companies that want to keep the information for 90 days, but then anonymize it. This often happens in web companies where they need to keep the information for a while to make sure there are no problems, but after that they want to get rid of it. Well, with column encryption, instead of keeping 2 copies of the data or rewriting the data after the 90 days, you actually can roll the keys every day and then delete the master key at the end of the 90 days, so that each day gets a new key, and after the 90 days, you just delete the old key. Once that data is deleted, once the key is deleted, now that data is inaccessible because you can't decrypt the local keys anymore, and so you've effectively given up access to that data. Now, how do we do this? We actually write both variants of the data. So we write the unencrypted masked data and the unmasked encrypted data. And we use the metadata to figure out which one we should read. We have to encrypt both the data and the statistics, because like I said, that index that ORC provides has the minimum and maximum values both at the file and down at the stripe, and actually even a third case of down to every 10,000 rows. So you'd actually get a lot of information if you didn't encrypt both the data and the statistics. We also maintain compatibility for the old readers. The old readers, because they don't understand encryption, will get the unencrypted variant. And finally, we had to preserve the ability to seek within the file because we couldn't afford to destroy the performance. Now, the streams go through a pipeline. They do run length encoding, that's required. Then they optionally get compressed, and then they do encryption. The encryption is all ASCTR, and we chose that particular version because it allows seek and doesn't require adding any padding. Okay, here's a question for you guys. Why did we do the compression first and then the encryption rather than the encryption first? Right, exactly. So once you've encrypted the data, then it can't compress. So you would end up making your files much, much larger. And so you'd make them huge. Okay, so the conclusions. So the encryption provides transparent encryption. It lets you get column protection and auditing with multiple paradigms. So you can access it from Hadoop, MapReduce, you can access it from Hive, you can access it from Spark. Everything will get the same protection and masking. You get audit logging, and you get the static masking. We also supported file merging. File merging is a feature for ORC where when you write little ORC files with Hive, you can rapidly stitch them together and to make bigger files. The integration with other tools, we're going to make, provide integrations with Ranger and Atlas, but Shrikant mostly covered that. Spark and Hive, they don't have any change other than defining the table properties. The one project that does have to deal with this a lot is Hive's LAP, and it's got to cache both the encrypted and unencrypted versions and keep those two differences. It also has to enable the audit logs and record who accessed which data, even if the data is already unencrypted in the cache. So what are the limitations? Right now, the Atlas and Ranger will scan the data to try and find the tags, but those tags come in after the data is already landed. And so you'll have to either put the policies in ahead of time, or you'll need to go back and rewrite the data to make sure it's encrypted. If you change the masking policy, you're going to need to rewrite the files because the statically masked data is actually in the files. We would love to have additional data mask ones that do format preserving for credit cards and addresses. And one of the ones I'm actually not that worried about is that you can keep the decrypted local keys, but because that is the local key for only the file that you actually already asked for permission to read from the KMS, it's not a big deal. So it does let you decrypt that data later, but you already had access to that data and you already logged as having read that file's data. So you basically have already put your fingerprints all over it. So the fact that you kept the key is not a big deal. All right, that's our presentation. Did you have any questions? Yes.
In Europe, we have this nice local GDPR.
Yes.
And one of the components in there is the right to be forgotten.
Yes.
And one of the solutions to implement that was discussed, is to have a encryption key per user, and then lose the key in case somebody wants to be forgotten. How do you move that direction, and perhaps do you have a better approach?
I would actually, for that one, well, first of all, the KMS is not going to be happy if you try creating a key per user, right? If you try to put 100 million keys into your database, that will become untenable quickly. And furthermore, that would put the KMS in the critical pipeline for reading your data. I think you're actually much better off using Hive's ACID and just doing the delete of the row. Arguably, we should do something else at the ORC level to support GDPR. One of my customers has talked about the ability to dynamically delete particular columns out of rows. Because actually, the interesting case in the case of GDPR, at least for that customer, is they don't necessarily want to delete the whole row. They just want to delete some of the columns out of that row. And so they're actually willing to let it mask it on read, and then the next time it's compacted, it'll be erased for real. And so I think that's a better approach, is basically either using Hive's ACID to delete it or to change it to be nulls for the fields you need to delete, rather than doing fine-grained encryption like that.
That would work if the data is mutated, but if, for example, in our example, it's click logs. Those are essentially immutable. And you don't change them.
Well, you could still turn a Hive ACID on. It doesn't cost you anything with Hive ACID v2. So actually, in that case, it would be fine. You could actually delete it just fine. Any other questions? Although GDPR is a great topic. We could talk, I think there are actually whole talks about GDPR at this conference. Yes?
So are there any plans to implement something similar for Parquet?
There are, actually. I haven't been following the Parquet work, but yes, I know there are JIRAs out there for people who want.
One issue I have with this approach is that all my clients have Cloudera legacy, and
So then they'd have to wait for the equivalent change in Parquet. Sorry. I can fix part of that stack, but I can't fix the whole stack. Yes.
So I was wondering, is this released already?
This is still in progress, so it'll get released soon. Yes. Yes, it does actually support nested structures, and you'd actually specify the column names going down completely into the nested structures. If you specify the top of the structure, it'll encrypt the whole structure. If you specify a sub piece of the structure, it'll just encrypt that part. No.
Do you have any customers that use that for PCI DSS?
Well, as I said, it's still in process, so we don't have customers yet. But actually, did you want to talk to?
Yeah, so the key is this. It's in the community at this point. We have not rolled this into any HTTP or CDH or CDP releases in the future. So a part of that is also all the work we need on Ranger, all the other components for this to work end-to-end for our customers based on the deployment scenarios. So what I want to show you here today is what's in the community. It's making its way through into a consumable release from Hotworks or Cloudera.
All right. Well, thank you very much.
Thank you.